Packages are collections of functions that we can add on top of Python to speed up coding and make our code more robust. Anybody can create a Python package and share it online, but how do we know which packages to use when we start coding in Python? Well, a good starting point are the projects sponsored by NumFOCUS, the fiscal sponsor behind the Jupyter Notebook, Python, and Scientific Python packages. In the NumFOCUS website, we can see the projects that constitute the core of scientific computing, for example, Numpy, which is the package for linear algebra, on top of which a large number of packages are written. Matplotlib, which is the package to create graphs and visualizations, and on top of which other visualization packages are created as well. Pandas to manipulate tabular data, etc. Then there are packages that are specific to research fields. For example, AstroPy for astronomy or QuantEcon for economical modeling. And finally, there are general and field-specific packages that are not part of NumFOCUS but are extremely valuable. For example, Altair for visualization using the grammar of graphics principles, Keras if you are into deep learning, SimpleITK to process and analyze medical images, and so on. To understand how packages work, let's take a quick look at NumPy, the linear algebra package, and Matplotlib for graph creation. If you're using Anaconda, these two packages are already installed. Every time we use a package, we have to import it, so we write import NumPy. NumPy is a short word, but sometimes packages have long names, so we usually give a package a nickname to be faster when coding. In the Python community, NumPy is usually abbreviated as NP, so we write import NumPy as NP. Now, let's say that we are working with a sequence of thicknesses. They can be any kind of thicknesses that you use in your field, for example, moon's crust thickness or knee cartilage thickness or tree bark thickness, etc. To create an array of thicknesses, we write thickness equals np.array and then open and close round and square brackets. In between the brackets, we add a sequence of numbers divided by commas, which I prepared before and I've just pasted here. Then, with the print thickness, we can see what's inside our array, and with type thickness, we can see that we are actually using a NumPy array. Now, a few useful commands to get started with NumPy. To know the dimension of an array, 1D, 2D, etc., we write thickness.ndim, and in our case, we have a 1D array. To know how many elements there are in the array, we type thickness.shape, and we see that we have 19 elements. Finally, to know the mean thickness, we type thickness.mean followed by open and close round brackets. As you can imagine, there are way many more functions and linear algebra operations that we can apply to NumPy arrays, and you will find all of them in the official documentation and in a large number of resources on the web. I will give you a few hints in the next video. As we said before, Matplotlib is the most common package to create graphs in Python. To import Matplotlib, we write import matplotlib.pyplot as plt, as usually done in the Python community. Then, for brevity, I've copied-pasted the code here already, but we're gonna go through it quickly and see what each line means. First, to plot the graph, we type plt.plot and open and close round brackets. Inside, the first argument is the x-axis, which in this case is an array that starts at 1 and stops at 19. You might remember from the previous video that the stop number is not included, with step 1. The second argument is the y-axis, which is the thickness array in our case. Then line style equals none, because we do not want a line connecting the dots here. And finally, we want red circles as markers. Then we add a string as a title to our plot using plt.title, and we add the strings for the axis labels using plt.xlabel and plt.ylabel. And finally, before showing the graph using plt.show, open and close round brackets, we use a small trick here to have proper ticks on the x-axis. In fact, if we comment out this line and run the cell, we get the ticks every 2.5 units, which is not very meaningful here as we are using discrete numbers. So we tell Matplotlib to position ticks where we defined the x-axis before, and in this way we get a meaningful graph. This was again just the basics of what one can do with Matplotlib. You can expand by browsing the official documentation, which provides plenty of examples and tutorials, and you can find many inputs and solutions on the web. So, in these videos I've shown you the very basics to get started with Jupyter Notebook and Python. From this point on, you can easily extend your competencies and create robust and useful code to make your workflows open and reproducible. As last thing, I would like to share some good practices for great scientific Jupyter notebooks using Python. Let's go to the last video.